Imagine a trampoline. It's flat, right? Now place a bowling ball in the center. What happens? The trampoline sags, creating a dip. This is a simple way to picture space-time. Space-time is the fabric of our universe. It's not an empty stage, it's an active participant in the cosmic dance. Massive objects like stars and planets create curves in space-time. Much like the bowling ball on the trampoline, this curvature is what we experience as gravity. The Earth orbits the Sun not because of some invisible force. It's because the Sun's mass warps space-time, creating a path that the Earth follows. Think of it like a marble rolling around a funnel. The marble is Earth, the funnel is the curved space-time created by the Sun's mass. This is how gravity works, according to Einstein's theory of general relativity. Before Einstein, we thought of space and time as separate and unchanging. Then came along this revolutionary physicist with a wild idea: gravity isn't a force. Instead, it's a consequence of the curvature of spacetime. Einstein's theory of general relativity, published in 1915, was a game-changer. It provided a new framework for understanding the universe. His equations showed how mass and energy warp the fabric of spacetime. Imagine stretching a rubber sheet taut and then placing a heavy ball in the middle. The sheet curves around the ball. This is similar to how massive objects warp spacetime. This curvature dictates how objects move through the universe. Planets orbit stars, and light bends around massive objects. It all boils down to the geometry of spacetime. Einstein's theory opened up a Pandora's box of possibilities, including the existence of black holes and wormholes. Now, let's talk about wormholes. Imagine folding that rubber sheet with the heavy ball in half. Now imagine a tiny tunnel connecting 2 points on the sheet. That's a wormhole. In theory, a wormhole is a shortcut through spacetime. It connects 2 distant points in the universe, allowing for faster-than-light travel. Think of it as a cosmic tunnel. Instead of traveling the long way around the curve of spacetime, you could theoretically zip through a wormhole and reach your destination much faster. But here's the catch: wormholes are still theoretical. We haven't observed one directly. Their existence is based on mathematical solutions to Einstein's equations. However, the possibility of wormholes continues to tantalize scientists and science fiction writers alike. Scientists are actively searching for evidence of wormholes. They're looking for unusual gravitational anomalies that could indicate their presence. One way to search for wormholes is by studying the behavior of light. If a wormhole exists between us and a distant star, the star's light would be distorted and magnified as it passes through the wormhole's gravitational field. Another approach involves looking for subtle ripples in spacetime called gravitational waves. These ripples could be generated by the movement of massive objects, including wormholes. However, detecting wormholes is incredibly challenging. They are thought to be incredibly small and unstable, making them difficult to observe directly. Despite these challenges, the search for wormholes continues, driven by the allure of unlocking one of the universe's greatest mysteries. The concept of wormholes has also sparked fascinating theories about the multiverse. The multiverse is the idea that our universe is just one of many universes existing parallel to each other. Some physicists believe that wormholes could act as bridges between these parallel universes. Imagine stepping through a wormhole and emerging into a reality completely different from our own. This idea is still highly speculative. We don't have any concrete evidence for the existence of other universes, let alone wormholes connecting them. However, the possibility of a multiverse is a tantalizing one, raising profound questions about the nature of reality and our place in the cosmos. Could there be countless versions of ourselves out there, living out different lives in parallel universes? The thought is both exhilarating and mind-boggling. The idea of wormhole travel is a staple of science fiction. Imagine zipping across the galaxy in an instant, visiting distant stars and planets. Wormholes could potentially allow us to bypass the limitations of traditional space travel. Instead of taking thousands of years to reach another star system, we could theoretically travel there in a matter of days or even hours. However, wormhole travel also presents significant challenges and potential dangers. Wormholes are thought to be incredibly unstable, and the gravitational forces involved could be immense. Imagine being stretched and squeezed like spaghetti as you travel through a wormhole. Not exactly a comfortable ride. Furthermore, there's the issue of navigation. How do you steer a wormhole? How do you ensure you arrive at your intended destination and not end up lost in some unknown corner of the cosmos? These are just some of the challenges we would need to overcome to make wormhole travel a reality. Wormholes remain one of the most intriguing and enigmatic concepts in physics. While we haven't found conclusive evidence of their existence, the search continues. Future telescopes and gravitational wave detectors could provide us with more sensitive tools to probe the fabric of spacetime and search for telltale signs of wormholes. Advancements in theoretical physics could also shed light on the nature of wormholes and whether they are stable enough for travel. The exploration of wormholes is a journey into the unknown. It's a quest to understand the fundamental nature of space, time, and the universe we live in. While wormhole travel may seem like the stuff of science fiction, it's important to remember that many scientific breakthroughs were once considered impossible. Who knows what the future holds? Perhaps one day, wormholes will unlock the secrets of the universe and allow us to embark on journeys beyond our wildest dreams.